Welcome to CVB101, the first law of thermodynamics. So in the last recording we talked about some of the basic concepts within thermodynamics, and we defined a few terms in mathematical senses like work and heat and things like that. We understand temperature, and we talked a little bit about units. So now we're going to talk about the actual laws, the laws themselves, the laws of thermodynamics. Now the first thing that we're going to talk about with respect to the laws of thermodynamics, the first law of thermodynamics, is going to have to do with internal energy. And so I'm going to have to explain to you a little bit about what internal energy is. So internal energy, which is usually given the symbol either U or E depending upon what textbook you're reading, is the sum of all kinetic and potential energies of all components of the system. So if that sounds complex to you, it is complex, and we can't measure the actual numerical value of the internal energy, but we can measure its changes. When the internal energy of a system changes, we can measure that. The change in internal energy after any process is called delta U, and remember what the delta means. From the previous recording, we talked about the delta of anything is equal to the final value of that thing minus the initial value of that thing when that thing undergoes some sort of a process. In this particular case, we have a chemical or a physical process in which the internal energy of a system changes, and therefore it's equal to the final internal energy of the system minus the initial internal energy of the system. So that gets us to the first law of thermodynamics, which says that energy is neither created nor destroyed. It is therefore conserved. Now there are several ways of looking at this. One of them is to simply say that the total energy of the universe is a constant. So if the system loses some energy, it has to be gained by the surroundings. If the system gains energy, it must have gained energy. The surroundings must have lost energy in order for that to be true. We can write this mathematically, that the delta U, or the change in the internal energy of the universe, is equal to 0. The change in the internal energy of the universe is also equal to the change in internal energy of the system plus the change in the internal energy of the surroundings. So then if we solve that equation for, say, the change in the internal energy of the system, then that would be equal to minus the change of the internal energy of the surroundings, which is pretty much just what I said, that whatever energy that the system picks up must have been energy that the surroundings lost, because the energy of the universe must remain constant. Okay, so the change in the internal energy of a system then is the sum of the heat absorbed from or transferred to the surroundings plus the work done on or by the surroundings. If you remember our definition of the system and the surroundings and so forth, we talked about the ability to transfer heat or to do work. And so this is the mathematical equation that gives us that. So the change in the internal energy of a system must be equal to the heat absorbed from or transferred to the surroundings plus the work done on or by the surroundings. Now we have to pay attention to the sign conventions. It gets really quite confusing. So the heat, if you have positive heat, it means that heat is flowing from the surroundings to the system. A negative heat means heat is flowing from the system to the surroundings. Now if that sounds confusing, the way it was explained to me once was if you think of your conical flask with your solution in it, and think of a little man in there. And if he's collecting heat from the outside, then the sign is positive. So he's like, if you think of heat as money, and there's a little guy inside your system. So if the little guy inside your system is pulling money from the surroundings, then the sign, he has a net gain, and so the sign would be positive. If he's paying it out to the surroundings, he has a net loss, which would mean that it's negative. I don't know if that helps you or not. It certainly helped me, but it's one way of looking at it. Work, positive work means work done on the system. Negative work means work done by the system. Okay? Much the same way, if you think of the little guy inside your system, if somebody does work on him, then he has a net positive, a net gain, so it's going to be, work is going to be positive. And if he has to actually do work on the system, then he's at a net loss, which means that the work would have a negative sign. So the delta U, a delta U that's positive means a net gain of energy by the system from the surroundings, and a delta U negative means a net loss of energy by the system to the surroundings. Okay? So another way to discuss the first law of thermodynamics is delta U is equal to Q plus W. So that is the internal energy of a system is equal to the heat plus the work. Energy can be transferred between the systems as either heat or work. So that's another way of saying what that equation is telling us. Now it's important to understand that Q and W are not state functions. They are dependent on the path of change. Now we haven't really defined what a state function is, which I'm going to do on the next slide. But basically, a state function is a function that depends only on the present state of the system and not the path on which the system arrived in that state, by which the system arrived in that state. So, in other words, if you stick a thermometer into a beaker and you measure the temperature to be 100 degrees, that's the temperature of the water in the beaker at that particular moment. So what you've done is you've described the state of the system. Okay? So when you can do a state function is a function that describes the state of the thing, but it doesn't tell you how it got there. There are many, many different ways you can get from one state to another. So in the example that I'm showing you here, where you have water at 100 degrees C and then you cool it down to water at 25 degrees C, you could have gotten there by taking water at 0 degrees C and warming it to water at 25 degrees C. So it doesn't matter which way you did it, whether you've taken cold water and heated it to 25 degrees or hot water and cooled it to 25 degrees. All you know is that you stuck a thermometer in it and it measured 25 degrees C. Do you see what I mean? There could be lots of ways to get here, but what you're measuring is the state of the system that you're interested in. Here is another way of looking at it. So delta U, that is the change in the internal energy, is a state function. But Q and W are not state functions because their values depend on the path that the system takes. So to give you an example here, if you found yourself in Dallas-Fort Worth, for example. Say you just woke up one day and you're in Dallas-Fort Worth and didn't know how you got there from Brisbane. You could have gotten there lots of different ways. You could have flown directly. You could have flown into LA and then taken a trip over a short hop from LAX to Dallas-Fort Worth. You could have flown to London first and then back around to Dallas-Fort Worth. You don't know how you did it, but you know that your current state was you were in Dallas-Fort Worth. Okay? Do you see how that works? State function. Now work can be defined simply as the motion against an opposing force. So, you know, we defined what work was before, and I'm reminding you of the units of force and so forth, units of force and pressure and volume and so forth. So the type of work that's most commonly encountered in a chemical system is the compression or expansion of a gas. So if we have a gas, in greater than atmospheric pressure, it's going to push the piston up until the gas and the atmospheric pressure are the same. Okay, and if you're doing work against the system is what you're doing, and that's called PV work. And when you do PV work, or pressure volume work, the work is defined as minus P delta V. And remember what the delta means. The delta is the final volume minus the initial volume. And pressure is the atmospheric pressure that you're pushing against. Okay? And then remember, when you're talking about PV work, you need to remember these units of force, which are going to be in newtons, units of pressure, which are going to be in pascals. These are both derived units, and the units of volume, meter cubes, and the units of work, like any other unit of energy, is going to be in joules. Now, heat capacity. Now, this is something that I mentioned in the first thermodynamic recording, and I was pointing out that temperature and heat are not the same thing. Heat is actually a transfer of energy due to a temperature difference, which looks something like this. Q is equal to C delta T, where of course T is a temperature, and you know what the delta means. There's a final temperature minus the initial temperature. And in this case, the C is the heat capacity of the thing whose temperature is changing. So if I had a beaker full of water, this would be the heat capacity for water. Okay? So it's related to temperature. Heat is related to temperature, but it really depends on the nature of the thing that you are heating or cooling. And this heat capacity is a constant that is going to be characteristic of the thing that's being heated or cooled. So a metal, which is a good thermal conductor, will have a higher heat capacity than something that is not a good conductor of heat. Now we need to talk about a couple of more definitions with respect to heat capacity. These definitions are not exclusive to heat capacity, but we're just encountering them now, so I have to define them for you. So a property that has a value that depends on the size of the sample is called an extensive property. A property that with a value that is independent of the size of is called an intensive property. So the heat capacity is going to depend on the size of the sample, and therefore it's going to be extensive. And in general, 4.18 joules are required to heat 1 gram of water by 1 degree Kelvin. This is, in fact, the definition of a calorie. This is why there are 4.18 joules in a calorie, is because calorie was defined as the amount of heat required to raise 1 gram of water by 1 degree K. So now you can take the heat capacity, which, remember, is characteristic. It's an extensive property, and it's got units of mass in it, right? Let me go back. So the heat capacity is in joules per calorie. Per Kelvin. So what we can do is we can change it from an extensive property by dividing through by the mass of the sample to get what's called the specific heat capacity, or sometimes called the specific heat. And now what we've got is joules per gram per Kelvin, and then Q is equal to the little c, which is a specific heat, times the mass times delta T, the change in temperature. Now we could divide instead by amount, which would be the number of moles instead of the mass. And you know the moles and the mass are related by the molar mass, right? So we can divide through by moles instead of by the mass of a thing, and we end up with what's called the molar heat capacity. Okay? All of these things are the way that we describe the relationship between the temperature and heat, because temperature and heat are not the same thing. Now, in order to determine heat, we often use something called a calorimeter, which is designed to minimize the heat loss between the systems and the surroundings. So a calorimeter is something like the Dewar flask that I mentioned before, the thermos bottle. A thermos bottle can be used as a calorimeter because it's very well insulated. It's a heavily insulated tank. Now, when you have a bomb calorimeter, that's also a system where the volume remains constant. The the Q of the calorimeter then is equal to minus the Q of the reaction. So what does that mean? Well, if I have a reaction that is giving off heat, then that heat will be absorbed by the calorimeter. So what we've got is like a system within a system. Or what we've done is we have insulated the surroundings away from the universe, if you want to look at it that way, so that anything that occurs inside this heavily insulated tank, any temperature change, is going to reflect the amount of heat that is produced or lost by the reaction, by the chemical reaction. Okay, that's it for the first law of thermodynamics. It was pretty short and sweet. We're going to get into concepts of enthalpy in our next recording, and I'll talk to you in a minute.